We are looking at the S21 of room temperature 3D cavity through a circulator on the network analyzer. The network analyzer cavities around 3.5 gigahertz. So let's go to what people usually do. The buttons people usually push are first log mag, hippy hip. There's a little blip. That you're going to trust me is the cavity. It's actually overcoupled, so the dip in dB is very small. Now, our aim is to then replicate this measurement with time domain hardware. But time domain hardware does not measure magnitude, it does not measure phase, it measures quadratures. So we want to go through and set this thing up to measure quadratures. So, but before we do that, I want to also advertise this is an overcoupled cavity, which means the dip in magnitude is very small. But it's overcoupled, so there should be a huge signal about the presence of the cavity. That signal can be super easily seen, especially overcoupled, by just going to the group delay button. If I push group delay, which is the derivative of the phase with respect to frequency, you get a super clear peak with a massive signal to noise ratio. That is a reflection of the fact that the signal is all in the phase when you're overcoupled with the reflection measurement. If you want, we can also look at the phase. Okay, now, so let's look at the phase. You say, oh, it should be in the phase, but oh, what the hell is this? It looks like some sort of crazy triangle wave, and I don't know what's going on. Oh my God. This is something we're going to need to correct if we want to look at the quadratures, because what you're seeing is the accumulated sinusoidal linear phase associated with the cables going from the device to the plane, reference plane of the device we want to measure. So that's why if I go here and just say, oh, I want to look at the real and imaginary part, I'm just going to see madness, right? I'm going to see wibbly oscillations, and I'm like, I don't know where the hell the cavity is. Oh, what's going on? Okay, what we need to do, if you want to, on the display of the network analyzer, get the real and imaginary part to look like they should according to the formulas, what you need to do is you need to correct what's called the electrical length. And now I have to remember what button. No, it's not the calibration kit.
I think it's at skill.
Yeah, so let's go back. It's not even really a calibration, it's just a button. Is it in scale? More. So it's all about this button, electrical delay. There's two buttons. Electrical delay will set a frequency dependent phase offset. The phase offset will set a frequency independent phase offset. In general, you're probably going to have to adjust both. So that's the real part looks like the real part of a formula in MATLAB or in Python, and the imagined part looks like. Well, okay, but let's first get rid of this electrical delay. The way this works, it's about 1 nanosecond per foot in a cable. So I don't know, I mean, I work in feet from the olden days. That's probably 1, 2, 3, 4, a foot. 3 feet is a meter. So this may be, let's assume this may be a meter. So it's maybe 30 nanoseconds. So then we can go here, 30 nanoseconds. No, I think I've gone, can I go minus 30? No, that made it worse. Okay, so my estimates are off, but let's go back to 0 nanoseconds. I mean, kind of a handy way to do this is just go 10 nanoseconds. No, they're getting pretty good. 15 nanoseconds. We might have gone too far. So actually, looking at the real imaginary part is not a great way to do this. The better way to do this is to look at the phase. So we're going to go to format phase. And you can see now it's tilting up before it's tilting down. You just need to adjust is it here? Electrical delay. I mean, I can even do it with the knob, I think. Right? You just adjust the electrical delay down. Okay, the knob is taking steps that are too small. Maybe 8 nanoseconds. No, then went too far. 9 nanoseconds. Now we're looking pretty good, right? Yeah, it's looking pretty damn good. Let's actually make the frequency range a bit larger, because then it's easier to see. Frequency start 4 gigahertz. It's easier to see the rolling phase. And then let's go back to scale. more phase offset. I mean, basically what you want to do, oh no, the phase offset. Let's set that back to 0. It's the electrical delay. Oh! See how flat it is now? Now it's mega flat. In fact, I think that's probably pretty good. So that is now looking flat, and now you can see, I mean, I'm looking at the phase. I don't know if this has a button for unwrapped phase. That'd be handy. Unwrapped phase, scale, auto, scale, all. Then you see what you expect. I mean, there's some wibbles in the phase, probably covering the cables and the directional coupler. But then you go to the resonance and boom, you have this big dip, big shift in the phase. That's why the electrical delay shows a peak, because the group delay shows a peak, because that's just the derivative of this curve. And the derivative of the curve doesn't care about the slope, of course, it is an offset. Okay, anyways, blah, blah, blah. Because we now have the phase flat as a function of frequency, that should get rid of the sinusoidal and cosinusoidal oscillations of the real and imaginary part. So if we go back to measure and look at real, we should see, okay, so if life was simple, the real would just show a dip and imaginary would show sort of the derivative of a dip. But now they're not quite the case. And that's just because not only do we have a frequency dependent phase, but we also have a offset phase. And that was the other button that you could correct back in the other software. So let's go back to measurement setup.
That's cool.
No, scale. So what I'm going to do actually, I'm going to go back, cancel, measure. I want to look at the real part, because I know the real part, if I get the correct offset phase, should look like symmetric dip. And then I'm going to go to scale, more offset phase, I don't know, like 45 degrees. No, maybe 90, maybe 80 degrees. Oop. Scale, more offset phase, 80 degrees, maybe. Looking pretty good. In fact, now I can, in principle, kind of use this knob, right? You can see it's getting more and more symmetric, and I've gone a little bit too far. It's asymmetric the other way. So the point, I'm going to guess, is about right there. And now my real part, maybe a little bit further. So you can see the offset phase I've needed on top of the electrical delay is then about 117.75 degrees. And now, if I go back, let's actually go back, oh, cancel, back, I don't know what I'm doing. Measure, no, sweep, I want a few more points, it's super low resolutions to 801 points. Right? And let's actually go. So you notice now on 4 to 8 it looks super nice, right? Mm-hmm. Because we've corrected all the electrical delays, actually you can see that the thing is bloody flat. We haven't even done any power calibration, normalization calibration. And if I go and push measure format imaginary, then we get a blip. Now actually the imaginary is the one that's sensitive to the phase. If you have a cable reflections, they show up earlier in the phase than they show up first order in the phase, they only show up second order in the amplitude. And so the imaginary part, which is sometimes called the phase quadrature because it's first order related to the phase, shows these wibbles, whereas the real part is nice and flat. The real part is, by the way, often referred to as the amplitude quadrature. And the other guy, the imaginary part, is the phase quadrature. So if we do everything correctly, including probably a software correction in Python with the plotting to correct for the electrical length of the cables, then we should be able to see something that reproduces this. Now, the only thing is that our analog bandwidth is, well, if we do the IQ modulation really and push the limits of our IQ mixes, we can go plus and minus 400 megahertz. Actually, the thing has a specified analog bandwidth of 200 megahertz, is it, of the keysight?
Yes.
Okay, so we can go plus or minus 400 megahertz. So let's just, for video, we can take a look at if I set my center to 7.5 gigahertz and my span to, so this is probably the next mode of the cavity, which is in the tail of the, where the circulator still works. Let's set the frequency span to say 400 megahertz. That's what we should kind of see if we do it properly and do the electrical length correction on the quadratures in Python for the real part. And then if I go to measure format imaginary, that's what we should see in the imaginary part. And so then the next question is, do we see that when we hook it up to our IQ up and down converter, which will be the next movie.